Now the next presenter is Schalk, Dr. Schalk. Dr. Schalk holds a PhD in probabilistic power systems modeling. He has been active in the subject of load research for over 20 years, and he will be sharing some of his knowledge with us today.
Maybe just to get a sense, like of the audience, like who's heard of him and beta and who's used it? Yeah? Oh, most people? Okay. Some people not. Yes, I started my career in as an electrical planner, and back then we used to use these diversity curves, and it fascinated me, how does these things work and so on. And I read this paper by Dr. Ron Herman, which he just published at that stage, and he said, well, you can represent the loads at the time of the peak with this beta distribution, and so we didn't cover stats as part of our undergrad. So I was fascinated by this and pretty much launched me into my load research career. So I wanted to find out how this works. So what are you looking at here is, so at the time of system peak, so don't ask me what is this time of system peak. We'll get to this later. But imagine there's this single point in time when the system is at its most loaded, right? And if you look at the individual household currents at this time of peak, you can draw a histogram of that, because that's the red bars there. And then Ron and Kritzinger basically went to this thing to say, fine, let's look at lots of statistical distributions for this, and they tried out a whole bunch of them, log normals, and obviously normal distribution won't work because, well, you don't get this negative load, so maybe we do now with electrical vehicles, so fine. And they kind of they settled on something called the beta distribution. And the beta distribution has certain characteristics, and I'll talk about that now. But it's characterized by 4 parameters: alpha, beta, the minimum, and the maximum. So actually only the minimum and maximum, if you think about it, because we can scale it using maybe the circuit breaker. Right? The other assumption that they made here is that this is constant current, and maybe not a bad assumption. Okay. All right, so this is the beta distribution. So I found this on Wikipedia last night. Okay, so I did a lot of preparation. So one of the cool things about the beta distribution is that it's almost like a little flexi curve, right? So depending on what alphas and what betas you give it, you can fit almost anything with it, as long as it's bounded. And obviously, if we have a circuit breaker, that's going to bound it. Now, the interesting thing we've observed, this orange line we've observed, we've seen loads, distributions like that. We've certainly seen the green line there. This red line here, I don't know who in the audience can think, when would that occur? So the red line there means it's sort of bunched to the one side, and then there's nothing in the middle, and then it's bunched to the other side. Who wants to?
That would be something like a solar PV.
Solar PV?
Supply. In the day.
Maybe think a lot simpler. Think a lot simpler. So at some stage, Eskom was experimenting with these 2.5 amp circuit breakers. So what actually happens then is that, it's pretty much an on-off type of situation. Either you've got something off or you've got something on. And you find that sort of red curve. So I don't think we've ever seen the blue curve. So maybe that's the PV thing that's going to come. I don't know. Okay, cool. So that's the alphas and beta. So, okay, cool. So what do we do with that? Okay, so there will be a test later. But basically what you're going to do is, okay. So there is a relationship between, very simply, between the ADMD, which everybody should be familiar with, the standard deviation, which I'll talk about now, but that's the kind of the spread of this thing, and the circuit breaker. And it looks a bit complicated, but if you sort of stare at it a while, you can put it into Excel and you can calculate alphas and betas. But that's not really what I want to talk about. Intuition here is that the alphas and betas is related to the ADMD, the standard deviation, and the circuit breaker. That's kind of the takeaway. Okay, so ADMD, and then if you take the design value, right, for let's say for a number of customers, and you start increasing the number of customers, you'll find that the design parameters sort of deteriorate. So who's worked with these coincident curves? We used to use. Okay. So what do you think is the difference between this and what we call the coincident curves? No? Okay. So, like, remember, this looks at one particular point in time, whereas coincidence curves obviously looks a bit wider than that. But it also has the same characteristics, so which means is when we start out, your design value might be 2.5 times the ADMD, and then as we add consumers to this, it slowly decreases, right? Okay, and this basic manipulation of the statistical properties is the basis for the Herman beta method. So it says, well, there's a mean value. We can do all sorts of things with means. There's some properties for that. We can transform it quite easily. And then there's standard deviations. And standard deviations also has some properties, how you can add them, you know, how you can, when can you multiply them, when can't you multiply them. But that's basically the basis for the Herman beta method. Okay. Cool. So now we want to get alphas and betas. We want to design networks, right? So what do we need? We need the ADMD, right? Cool. We need the circuit breaker. We kind of decide that actually, maybe. And we need to know something about the standard deviation. So those are kind of the 3 parameters we need to know, right? So now I'm going to tell you, gives you some intuition as to, you know, what do we do with that? So so each of these dots here, I think is similar to what Rob showed before. Each of these dots here represent about 60 consumers in different, you know, places across the country, different socioeconomic conditions. And you don't have to be too artistic. Just imagine there's a line there, right? Sorry, Marcus. So, and then if you're a design engineer, like when I started, the guy said, like, hang on, guys, this is quite simple. All you know roughly like a load factor, and if you know what the consumption in the area is, you know what the ADMD is. Okay, so that works out more or less okay, except maybe there's a bit of a constant to this line. But like it generally holds, and then, I mean, the intuition is there. So like obviously the more the consumption and these loads kind of scale towards it. There's a bit of fuzziness here, and I'll talk about that now, a bit later. Okay. All right. At that stage, I got introduced to Marcus. So this was back in '96, I think, Marcus. And Marcus gave me like the CD. This was like fantastic. On the CD, there was these CSV files. Right? So it's not big data, it's like a CD, right? And on the CD, and I remember I had to buy my own CD because like, this was like a special like CD, right? And on this, there was like CSVs, there was like 5-minute load readings on there. There was questionnaires. So what they do is they go to each of the households where they put this meter up. They ask them a whole bunch of questions. Fantastic. Now I'm armed with this thing. And that was the start. I think at that stage you were running for like about 2 years or 3 years. This was the start of the NRS domestic load resist program. So in this big collection, 10 to the 12, I think what they said. There's amps, there's voltage, there's now kilowatts, there's kilowatt hours, kVAs and so on as well. But when I started, it was amps and voltage. We know something about customers' demographics. We know about appliance ownership, alternative fuels. In other words, do they use wood for heating or for cooking? The nature of the electricity connection, basically the circuit breaker. We know also like which questionnaire belongs to which household. And then obviously if you talk to the Weather Bureau, you can find out something about the temperature and the rainfall and sunrise, sunset of these places. Cool. So if we then take all of these things, so the first thing we did is like we kind of, like the first thing I did, I kind of did this tree regression. I found this in the 2001 report, but I remember back in 1996, 97, we also did this. But basically, if you okay, so the intuition, like how this thing works is, it says, so left and right. So left, if the household income is less than this, go this way, and if the household income is more than that. And you can sort of see the important things here to notice is the household income, the geyser number, there's something about appliance ownership, sort of breaks down, and like how many people do I cook for, and so on. And then like later on, like 2010, we did another one. As you can see, floor area came out like quite big. So to your intuition about the floor area size, the number of geysers seems to be important. The income, and so on. Okay, don't spend too much time on that. So now what we can do is we can say, okay, fine, let's take the income rand per household per month. We can take the consumption, and we put it on the log axis, and you can see, well, there's kind of a relationship happening here. Like we can ignore those outliers, Constantinos. Just ignore them for now. We'll come back to them later. All right. Anyway, so there's definitely income is happening. This is quite an interesting one as well. So what we've got here is the floor area of the house, the consumption. So Marcus spent a lot of time like standardizing how do we measure the floor area of a house. It's kind of tricky. Like if you think about, like if you think of your own house, like how would you measure like does it include the garage or does it not include it? What about the lapa there by the pool? You know, what's included, what's it? They've got a nice standard definition for that. So what you see is there's a portion here where load and floor area is not strongly linked, and then it sort of goes off. Okay, so it's a bit of a non-linear relationship. The other thing is like in terms of the number of geysers. Obviously, you see like initially there's load, it's not geyser related. And you get this sort of flat piece here, which is kind of interesting. I'll talk about that now, and then you get this nice linear piece there. So what was happening here is like we found this like geyser ownership, especially with the lower income areas. Like you might have a geyser, but like if the thing is broken, you know, not serviced, then like, it doesn't actually add to the load that much. I'm going quite quickly through some of these now. The other one that we saw is like the income to geyser penetration. All right, also some relationship. I don't want to go too deeply. Then the other impact was in terms of free basic electricity. So this was a study done, a nice A/B testing and control group treatment group. Found a community two communities that are similar. On the one side, free basic electricity was piloted. The other one, there wasn't. And we sort of came up with this curve that says consumption and some price elasticity as well. So all of these things I'm skimming over. Marcus will talk to you guys about in, when is it? October? When is your next talk?
Just now.
No, the one in October. So
30th of October.
30th of October. So please attend the one on 30th of October if you want to know more about this. I'm just sort of skimming. Hey?
It's not the rand we want.
Fantastic. Monde?
It's free.
Free. It's going to be free. Next time we'll pay you to come. Okay. All right. Okay, but I mean, if you, so we came up with a sort of a causal model. I mean, like to say, you know, household income drives, is there water in the place or not? Like, you know, do you own a geyser? What about your other appliances? Do you use them? The floor area. So one of the interesting things about floor area was like, if you earn a lot of money but you stay in a very small house, like you don't use a lot of electricity. I mean, you've got your basic needs. So there's something else that happens there as well. If you load limit customers, obviously limit the appliances that they can use, but also ultimately their load. The tariff that they're on would influence that as well. So we sort of came up with this sort of basic model. And then we fitted a model to it. So the model is got an R-squared of 87%, so that means 87% of the variation in the source data is explained by the model. It's not too bad. It's got a standard area of about 80 kilowatt hours. Okay, so that's the basic model. And then if you take a slice out of that, just give you a sense, because remember there's like all these non-linearities in there. So you find like if you take a slice of income, you take a slice of consumption, you can see it sort of does this sort of weird curve, and then you can do it. So this is at 7 years, you can do it at 15 years, and you can. So now we've got a sense of what the consumption is. We've got modeled parameters for that, and basically, I mean, this model is then driven by, you need to know what is the household income. You can adjust it for the floor area. You can adjust it for free basic electricity, and then time electrified. So it gives you the roughly that. Okay, cool. All right, now back to the Monde. So remember, this whole sidetrack was to say we want to know what this ADMD parameter is. Okay, so we've got the consumption we can predict now, and we've got ADMD, but there's still this fuzziness. So like, how do we going to deal with the fuzziness? All right, so when we started, Marcus came up with this idea. It said there's something called Climatic Severity Index, something like Marcus just invented, right? And it said like the different areas have got different climatic severity indexes. So like Durban is a -1, and Cape Town is a +1, and everything else is sort of like in between, right? There's some measurements as well later on to say, well, like there is something about temperature, so temperature in different areas, maybe sunrise, sunset as well. So this is the 6 o'clock, the load. You can see, obviously the slope of the load is, varies. Maybe in Durban it's like less pronounced than in Moroleta Park here in Pretoria. Okay, cool. If you take all of that together, we can explain more some of that fuzziness way. Say we can do an R square of 97%. So 100% is full marks. I've got 10 minutes left. I need to speed up. And I can predict now the ADMD. And what I can do is, like using a similar process, we can also predict the standard deviation. Okay, cool. So we've got now all of the parameters. Skip this slide. All of the parameters. Okay, so now remember this is a probabilistic design method. So how it works is we give it a distribution of loads in and we're getting a distribution of voltages out. Or distribution of currents if you care about transformer sizing. Okay? So one of the things you have to decide is what is the confidence level at which you're going to do this, right? So, we kind of said, well, there's confidence and there's like the inverse is the risk. So there's a 10% risk that you can exceed the voltage if you use this method. And up to now, like I'm sure in SANS it also says like just use 10%. Like no real explanation of what that means or what the implication of the 10% is. Okay, so now I'm getting back to the thing to say, well, remember this talks about the load at the time of the peak, but like which peak? Okay. So actually, if you look at a particular, like any week, what you'll see is like there's actually a whole bunch of peaks. So like which peak are we actually talking about here? All right. So that might be the one that we use the Herman beta method for, but like there's a whole other ones. And then the assessment methods for whether your networks are performing or not doesn't look only at that one peak. It actually looks at this whole week or like any particular week. And there's 3 criteria for it. So the one looks at any instantaneous 10-minute supply. So that's plus or minus plus 10%, minus 15%. Then there's another criteria that says, well, on every day, throw away 7 of your 10-minute readings and look at the 8th worst one and record that for comparison to the compliance levels. And then there's another one, like if you read a couple of paragraphs later, there's like a fine print that says, oh, and also look at any 2 consecutive periods. Like in any 2 consecutive periods also needs to be compared to the compliance levels, right? And you need to do this for a week, and if there's longer term measurements, there's like procedure for that as well. Okay. But actually what we found is like if you take the load, we did this across a whole bunch of networks and so on, there's like one of the criteria dominates, and that's a 2 consecutive periods. So that's the yellow line there at the top. So if you can meet the 2 consecutive periods, you'll meet the other ones. And if you fail on the, if you can meet it, then that's fine. So it actually simplifies down to 2 consecutive period measurements. Okay, so now this is the question. So if we're designing for 10% risk, in other words, we're saying, 9 out of 10 times our network is going to work, 1 out of 10 times we'll have to go back and go and fix it up, maybe after 7 years, after 6 years. So what is the risk then of quality of supply violation? So we launched into the study. In 1997, so this was my master's research that I did. It looked like about 20 to 30%. So if you design for 10%, so 1 out of 3 times you'll actually have a violation. So you were hoping to get 1 out of 10, you're going to get 1 out of 3 times. Okay? So and then I had an opportunity to go and measure some of these things and see how well it works and test that theoretical desktop study of mine. So with Lloyd's team, we went to some of the load research sites, and we got the as-built. Actually, we got like consultants to go and survey the network, so the as-built network as it was built. And then we said, okay, we've got load research loggers at certain points in this network. One of the things that's not there when they do these surveys is what is the phase. So what phase is this house connected to? And I'm sure you understand this is like quite a crucial parameter. And this was the time when like Arduino, well, I was introduced to Arduino, so I said, let me build a phase detector. And you can see it's got this cool antenna on it, and it's like really bad. And it's like this big 9-volt battery on it. But like we went to some of these sites and we did the phase allocation. So basically going from house to house, like plug it into the outlet and say, what is the phase of this house on? So now we've got a full picture of the network. We know the conductors, we know the transformers, we know what the phases they're connected on. So cool. And then we said, okay, fine, let's look at some of the sites and look at the number of quality of supply violations that we've got there. And there was actually quite a lot. Right? So we said, okay, hang on, what went wrong? Maybe this Herman beta method wasn't so smart after all. Okay? One of the things that like if you look at some of the loggers that were closest to transformers, you can see this massive like MV supply drop, right? Okay, so fine. So maybe not the Herman beta, maybe there's something else happening. Yeah. So there's some practical things about MV supplies. I think Justice is going to talk about that later on. So you need to know about that as well. Okay. So now we said, okay, fine. We've got all these measurements, limited number of sites, but you still want to answer this question. Like, if I design for a 10% design risk, what is the risk of me getting the quality of supply? Because I need to we need to give this method some risk value or some confidence value to get the design value. So I'm going to design this Monte Carlo simulation, and basically the idea is that I've got the actual networks there. I've got loggers of some of the houses on these networks. And then what I would do is I'd take those 5-minute amp or current streams, and I would put it through like basic Ohm's laws, calculate what is the voltage at the end of that network. Very simple. Once I've calculated it, apply the NRS 048 criteria to that. So how's the voltage performance of this network? And then I repeat this 1,000 times. So I say just like, let's just assume we can move these houses around and so on to get a sense of the distribution, because obviously those networks we're looking at one particular case, and we want to get to a general version of that. Okay. Okay, and then so these are some of the results. So that's the network. You can see the blues, then the distribution you get, because when you're doing this 1,000 times and you're randomly assigning, you can get a distribution of NRS voltage performance. And then the red line is the actual. This is for a different site. The red line is also there in the middle of the distribution. A last one, another site. And you can see these houses, these communities are very different from each other. But every time, so it gives us some confidence in this method. So we've now verified that if we apply this Monte Carlo type of simulation, and what we actually measure kind of tie up. Okay, cool. So now what we want to do is to say, okay, we're still trying to answer this question. What is the quality supply risk versus the design risk? I applied it to a whole bunch of different type of networks, some of them balanced, some of them unbalanced, some of them from the benchmarks, the NRS 034, it's got a whole bunch of benchmark networks, applied those, applied some of the actual ones in there. And so my conclusion is that the quality supply is roughly 2 to 3 times the design risk. So my master's degree vindicated, yeah. So we see that, but it doesn't hold for high imbalance. So then maybe we've got like a high imbalance network. It actually, the Herman beta method tends to like over-design. So there's something about the way when we're dealing with long pieces of network, single-phase networks, it doesn't, but in general, we're going to balance them, so fine. I'm happy with that. So we're saying it's like a 2 to 3 times. So logically, if you want to get the 10% risk of, so 1 out of 10 of your networks to work, 9 out of 10 to work, and the one you're going to go and fix up. What you need to do is you need to reduce the design risk then to either 3% or 5%. Okay? So independently from this work that I did, Professor Gaunt at University of Cape Town did like a very different study looking at the beta parameter distributions and like quite a graphical method. And I won't be able to do justice to what we've done. But the conclusion from that study, which was then published at SAIEE, I believe, is that also like the 5% is the design risk to work for. So I think that's kind of the takeaway. So independently verified 2 completely different methods, also through measurements. So here's my summary. So Herman beta method looks at a single point in time. Right. We can get the ADMD, we can get the parameters for that from where it is in the country and the ADMD. And ADMD we can roughly get from the consumption. So if you purely want to do a lookalike thing, you've got houses with a certain consumption, and it's roughly the same area. That's probably okay. you probably want to adjust it for local conditions. So the densification we spoke about, theft, load growth, all these practical things. You need to factor that in. And you want to use a design risk of 5%. So that will give you like the 1 out of 10. I think there's a whole other question about like, should it be 1 out of 10 or 1 out of 20 or 1 out of 5? And that becomes like a cost of supply, cost of build, cost of like how much does it cost you to go back? Are you building these networks like super robust? If it's cheap for you to go back, maybe you can you can reduce that or increase the risk a bit because it's fine. You're just going back and fix the ones that are working. Or if it's like really hard to get to and it's super expensive, you probably want to increase the risk. You can kind of play with that and it becomes like an engineering costing exercise. So thanks, Monde. That's...
Quick one. I understand the 5% risk and the 10%. And of course, if you're a consultant, you're going to put a 20% risk on, and if you're a municipality, you're going to put a 0% risk. However, did you actually compare that to what you've chosen, alpha and beta? Because you can skew that thing big time. You can say, everybody's going to use 20 amps as opposed to 50 amps, and I'm going to push this thing left as opposed to pushing it right. Or push it right, hey, I'm basically designing at -5, as opposed to being more appropriate. So did you actually link this to the choice of alpha and beta?
Yeah, so in that study, I kind of cheated, because what I did is when we went there, we measured the actual load. So we said, let's assume you can predict this load perfect, right? We really wanted to look at the statistical properties of this method. The risk of getting it right or wrong, so that's the standard areas and the R-squares I was talking about before, so you can bring some of that in. But then there's also engineering, I feel, that says, well, like you'll get lots more houses, or like theft is a big problem here, or whatever the case may be. So that's not 100%. That's not part and parcel of that risk. This looks at only the probabilistic nature of the loads that we give, not the rest of the world.
If it was a high theft area, would you push the graph to the left, to the right, in other words, to the maximum of the circuit breaker size?
Well, the other question is going to be, is that circuit breaker even going to hold? And we just put in bigger circuit breakers when they, or do we just take those things out and put some wire there? I don't know.
AEMs, okay. So we're stuck at AEMs. So at least you're not talking about a meter curve. It's quite a finite.
Yeah.
Otherwise, we'll be back to square one.
So typically what's going to happen is your ADMD will move up. Right? As the ADMD move up, the spread also moves up, so that the standard deviation will move up, and it will slowly get punched more towards the one side. But apart from that 2.5 amps, I don't think people, the load ever gets punched up, because logically, if your circuit breaker keeps on tripping, you put a bigger one. This is not hard stuff, right? It's not like
When you take it away completely.
or you take it away.
Did you have an opportunity to have a look at the impact of what appears to be high numbers of unofficial bridge connections and things like that, which obviously got a different random component to them?
Yeah, not at all. So, like I said, we kind of ring-fence this thing, but those are the practicalities of it. You get this growth, there's a city planning type of thing, there's the migration, and those factors probably completely outweigh the type of stuff that I'm talking about.
Yeah.
Because this is the reality of electrical engineering, right?
Are those essentially regionally dominant, large city fringe areas and things like that? They're not so common in the remote rural type environment.
I think that's what Rob suggested in his talk. I don't know, Rob, do you want to comment? So it has to do with the densification, in urban versus maybe deep rural.
I mean, when they come into That's just, I don't know any answer to that. You just got to have a look at trends in the area. And then, because not each of the backyard shacks are going to equal the same as the, so you might say, look, the normal place there says 1.5. I know that some of them are using instead of 1.5, 1 kV 4 kV load. and then just design for that, and then say that, look, hopefully we get saturation. You can't put a lot of appliances in there anyway from that. But it's not exact science at all.